In previous videos, we use sample statistics such as the sample mean, sample standard deviation, and sample variance to describe data we actually observed. Those statistics summarize the center and spread of a sample. Now we shift our focus to probability distributions, which represent the population or long-run behavior of a random process. Instead of summarizing observed data, we summarize the distribution itself. These summaries are called parameters, and they describe the underlying process that could generate data. A probability distribution tells us how likely each possible outcome of a random variable is. Because it describes the process before data are observed, the numerical summaries we calculate from it are population quantities rather than sample statistics. This distinction is important. Sample statistics vary from sample to sample, while parameters describe the theoretical distribution that governs the process. Understanding this difference helps connect probability models to real-world data collection. It is common to use different notation for sample statistics and population parameters. The sample mean is written as x bar, while the population mean is written as the Greek letter mu. The sample standard deviation is denoted S, while the population standard deviation is sigma. Likewise, sample variance is S squared and population variance is sigma squared. This notation reminds us whether we are describing observed data or the underlying probability distribution. The mean of a probability distribution is called the expected value. It is written as E of x or mu. The expected value is a weighted average, where each possible value of the random variable is weighted by its probability. Mathematically, we compute it by summing each value multiplied by its probability. Conceptually, the expected value represents the long-run average outcome if the experiment were repeated many times. Let's look at example 1 involving the Florida Lottery Pick 3 game. You pay $1 to play. If you lose, your net result is negative $1. If you win, the prize is $500, but after subtracting the $1 ticket cost, the net gain is $499, and the probability of winning is only 0.001. We define the random variable x as the amount of money gained per play. To compute the expected value, we multiply each outcome by its probability and add them together. The calculation gives negative 1 times 0.999 plus 499 times 0.001. The result is negative 0.5. This means that in the long run, a player loses about 50 cents per ticket. The expected value does not predict what happens on one play. It describes the average outcome over many plays. Now consider the Pick 4 game. The structure is similar, but the prize is larger and the probability of winning is smaller. Losing still costs $1, while winning yields a net gain of $4,999. When we compute the expected value using the same weighted average method, the result is again negative 50 cents per play. This illustrates how lottery games are designed to produce a negative expected value for players. The interpretation of expected value is crucial. It represents a long-run average, not a guaranteed outcome. A person may win or lose on any single play, but over many repetitions, the average gain approaches the expected value. This is why expected value is so useful in decision-making and in understanding systems like gambling or insurance, where outcomes vary but probabilities are known. Example 2 looks at life insurance. An insurance company sells a 1-year policy for $290 and pays $10,000 if the customer dies during the year. The probability of death is 0.001. We define the random variable x as the company's profit per policy. If the customer lives, the company gains the full premium. If the customer dies, the company experiences a large loss because it must pay the claim. Calculating the expected gain uses the same expected value formula. The profit when the customer lives is weighted by the high probability of survival, and the loss when the customer dies is weighted by the small probability of death. The resulting expected value is $280, and this illustrates how insurance companies rely on probability distributions and expected values to set premiums that yield positive long-run profits. While the mean describes the center of a distribution, we also need a way to describe spread. The variance measures how far values tend to lie from the mean. It is computed by taking each value's squared deviation from the mean and weighting it by the probability of that value. Squaring ensures that values above and below the mean both contribute positively to overall variability. The standard deviation is the square root of the variance. Taking the square root returns the measure to the original units of the random variable, making interpretation easier. The standard deviation describes the typical distance between values of the random variable and the mean. Together, the mean and standard deviation summarize the center and spread of a probability distribution. In example 3, we revisit the allele copy distribution from a previous video. The random variable x can take values 0 through 3 with specified probabilities. To compute the mean, we multiply each value by its probability and sum the results. The calculation gives an expected value of 0.75. This means that on average, a plant carries 3/4 of an allele copy across many observations, even though individual plants cannot have fractional copies. To calculate variance, we first compute the squared distance between each value and the mean of 0.75. Each squared deviation is then multiplied by its corresponding probability. These products represent contributions to the overall variance. Organizing the calculation in a table helps keep track of each component and makes the computation clear and systematic. Adding the contributions gives a variance of 0.7875. Taking the square root produces a standard deviation of approximately 0.887. This tells us that values of the random variable typically differ from the mean by about 0.89 allele copies. The standard deviation provides an interpretable measure of variability around the center. An important point is that the mean and standard deviation summarize the distribution rather than individual outcomes. The mean may not correspond to an actual possible value. For example, no individual plant can have exactly 0.75 copies of an allele, but the average across many plants can be fractional. Parameters describe long-run behavior, not single observations. The big picture is that expected value, variance, and standard deviation extend the ideas of center and spread from sampled data to probability distributions. They allow us to summarize entire random processes mathematically. These concepts form the foundation for much of probability and statistics, including prediction, risk analysis, and statistical inference. Understanding them helps us connect theoretical models to real-world variability,